since 10 years ago or more, it represents a significant change. So a long time ago, when I first started at Argonne, I was programming GPUs, and I think the first version of CUDA I used was version 1.2. So I was slower than some of my friends. But back in those days, the only programming model that existed for GPUs was CUDA. You wrote CUDA C if you wanted to run it on a GPU, and otherwise there was nothing. And that was okay for the people who were willing to do that. But it meant that the results that people got, there were a lot of people who just couldn't do that for whatever reason. And we've made tremendous strides in programming models and in algorithms and applications over the last 10 years. And where we are now is we still have CUDA. There's no question that CUDA is the best way to program a GPU, an NVIDIA GPU, of course. It's the best way to get performance. CUDA will always have the latest and greatest hardware features exposed in the most effective way, and we will innovate as fast as the hardware moves in CUDA. But what is new and very important for everyone to be looking at is there are now two other pillars of GPU programming that are well supported on the NVIDIA platform and which offer a very favorable trade-off in terms of productivity relative to performance. They don't always hit the same performance. CUDA is always going to be the speed of light, but there's many cases where they do perform just as well. And when they do, you get the performance you want for less effort. And the two pillars, so the one in the middle is directives. And this is obviously familiar, I think, to many. There's OpenMP, which have been directives, for 20 plus years, starting with CPUs and of course with GPU support more recently. And NVIDIA does support OpenMP for GPUs. We don't think that it's the best model, but it is the model that the community has pushed towards for if you want to have multi-vendor support. We also have OpenACC, and OpenACC has multiple implementations, but doesn't have all the vendor support that OpenMP does. But OpenACC is a very well-established, mature technology for programming with directives in C and Fortran and C++. And CUDA is the same way. CUDA has Fortran and C++, and you can even do Python CUDA now there's a project called CUPy. Now, the one that's newer and the one that everybody should be thinking about as they move forward and as they think about what's in this talk is NVIDIA is bringing the GPU level of performance and parallelism to the standard languages. And when we say standard, what we mean is the ISO standards. So there's ISO standards for all sorts of things. There's ISO standards for program management and for electrical signaling and all sorts of stuff that I don't even understand, automotive safety, everything you can imagine. ISO stands for International Standards Organization, and they are the people that standardize things for everybody on the planet to use. And that is the absolute ground truth in terms of maximal portability for all the platforms. And what we have done over the last couple of years is invest heavily in making sure that you can use the ISO standard parallel features in C++ and Fortran and run them on GPUs. And what I'll show in this talk is a number of examples where you can write ISO standard C++ or ISO standard Fortran and run it on an A100 GPU and get amazing performance with the exact same code that you run on other processors, whether they're CPUs or any other platform that supports the ISO language parallelism will support this. And this means that there is no divergence in your code. You don't have to think about CPU versus GPU. You don't have to think about different vendors. Obviously, if vendors don't want to support standard languages, there's nothing we can do about that. But obviously, there's many compilers out there that support ISO Fortran, ISO C++ on CPUs. And then as other people catch up with GPU support, they'll also be able to take advantage of this, the code that's written in this way. But these three pillars represent three different levels of control, three different levels of portability, and three different levels of performance. And what I think everybody should be thinking about is how they can take advantage of these different levels and how they can compose them. And this is the other part of this. This is not a pick your pillar and you're stuck. This is a start with the one that makes you happiest. If you happen to have a legacy code that's all CUDA, great, keep using CUDA. If you're happy with CUDA, no problem. If you want the absolute maximum performance, use CUDA. If you want to have the most standard parallel thing you can have, well, then start on the left column and start with standard parallelism. And what you'll find is standard parallelism, by virtue of being a standard and being a little bit slower moving than some other things, will not necessarily have every single feature. So asynchronous offload is something that currently doesn't exist in Fortran standard, for example. I'm working on that, but it's not there yet. So you can add some directives to standard parallelism to get some of that asynchrony or get more control over data movement. And then if you have an application, molecular dynamics is a great example where people just really, really want performance. You can use you start with standard parallelism, you can add some directives, and then you can drop in CUDA if you really need to go at the speed of light. And so this is something that in our compilers for as many of the languages as we can, so C and C++ for Fortran and for Python where it makes sense. Obviously directives in Python doesn't make sense, but we have Python support for standard parallelism through NumPy, and then we've got CUDA Python. We've got all that support, and I want everybody to be thinking about how they can mix and match these in application development to get maximum portability and maximum performance based upon their characteristics. There was a hand up. Is there a question that remains? Yes, Priyanka. I don't know how to. Somebody, can the organizer unmute her, or how does? I can't unmute the person who's raising their hand.
She has to unmute herself. We have not used my unmute.
Okay.
Priyanka, if you have any question, you can ask now. Or I will rather ask the participants to hold on till the end of the presentation, and we might take a short break after Jeff's part is over, and then they can ask the questions.
Okay, that's fine. Just save your questions, and hopefully we'll get them all. And if not, you can always email me. Okay. All right. So here's the ecosystem, and this is just to emphasize that there's a broad spectrum. NVIDIA is been growing the support from in the old days when I started, there was CUDA BLAS, and now there's cuTensor and Sparse and all this other fun stuff. There's obviously the machine learning libraries, which didn't even exist when I started, which is crazy to think that I'm that old. And now, of course, NVIDIA is, Mellanox is part of NVIDIA, and they have their own set of networking software, which is now being integrated with the GPU side of networking with, NVLink. So NVLink plus, GPU Direct and all that stuff with Mellanox is giving us a very rich software stack that includes the network as an important component of our software stack, and this stuff will continue to will grow. And then we have obviously the tools that go along with that inside in the debugger. So anyways, all this stuff is there, and as folks probably know from our GTC presentation, we're getting into ARM in a serious way. NVIDIA has actually been doing ARM for a good long time, and some HPC codes were in fact ported to ARM first on an NVIDIA ARM chip a long time ago. But now it's obviously a much more serious thing, and you can imagine that ARM support is going to be really critical to our software in the future. So please look out for that. So let me show this example. This is from this source code is from Lulesh. Lulesh is a hydrodynamics, which is sort of a fluid dynamics algorithm from Lawrence Livermore National Lab. This is on GitHub. I believe that blog post, if it doesn't link to it, it links at least to the content describing this set of features. But if ping me if you can't find Lulesh on GitHub. But what we have here is an example where using ISO C++ parallelism is not just a good thing for performance, it's also a good thing for readability and productivity. So on the left, you have the OpenMP code with directives, The algorithm here is very simple. It's MapReduce. It's one of the most famous algorithms in the world, and it turns out, at least in the way Lulesh was written, MapReduce wasn't a first-class citizen in OpenMP, and I guess you couldn't write the code directly, so they had to add all this extra stuff. Well, it turns out, thanks to the C++ parallel algorithm transform reduce, which is MapReduce by another name, you can implement this same piece of code with fewer lines. And as we'll see in just a second, the performance is fantastic. So obviously the performance here, the primary reason for the big green bar on the right is that the A100 high bandwidth memory is significantly more capable than anything you can get attached to a CPU today. But it's not just that. You can also take advantage of multi-core parallelism. And this is just showing our compiler versus GCC's. GCC is, of course, a fantastic reference compiler and does a good job with C++, and they have a parallel STL implementation. And this is just showing, hey, you could do a good job on CPU too. You're not compromising by using standard parallelism. This is not, this is not somehow standard C++, but it only runs well on a GPU. This is standard C++ code that, as you can see here, is faster than the equivalent OpenMP code on CPUs and is advantageous to use our compiler. So this is the best of all possible worlds. You write less code and you get more performance, and you get more performance in the CPU case relative to OpenMP, and you get more performance in the GPU case relative to the CPU. This is another algorithm. This is a Lattice Boltzmann. So this is important because this comes from Professor Jonas Lott in Geneva. And obviously, he's not an NVIDIA employee. So this is just to make it abundantly clear. This is not, anything I'm talking about here is not just for, experts in GPU programming or NVIDIA employees or something like that. This is something that anybody can pick up because it's ISO C++. It's if you're using C++, you're already familiar with this. This is a standard template library set of algorithms and now running in parallel. So this is, they're clearly getting a fantastic result here. 12x speedup is once again primarily coming from the memory bandwidth capability of GPUs, which is generally speaking vastly superior to CPUs. But once you take advantage of the abundant parallelism and bandwidth that exists on the GPU, the code goes really fast using without resorting to CUDA. Right? There's nothing CUDA-ish about this. This is just standard C++ running on GPUs. And now I'll switch. I've said C++ too many times. I got my start in Fortran with a code called NWChem. I still work on NWChem and I enjoy it quite a bit. And this is just demonstrating the exact same type of success with the ISO Fortran standard parallelism. So there's a blog post written by my colleagues all about this. You can follow that link and catch the details. So everything I talked about, this is in the release version of the stuff. This is not preview. This is not please wait till the end of the year for this compiler. This compiler has been shipping since I joined the company in March, and I've been using it since day one. So what you see here is ISO standard parallelism in Fortran. This took me, I think it took me 6 minutes to actually write this code. I did a search and replace on the original Fortran 77 do loops and replaced them with do concurrent. And then the code runs significantly faster than the CPU version. I will also say that the GPU version of this code runs better with Fortran standard parallelism than with OpenMP. It beats OpenMP by like 1%, and it's probably a weird compiler artifact, but it beats OpenMP by a significant amount. And the reason is that OpenMP is a prescriptive model. And what that means is you tell OpenMP what to do, and it does it. And if you tell it to do the wrong thing, either generate too much parallelism, too little parallelism, or the wrong type of parallelism, the compiler will do exactly what you told it to do and nothing more and nothing less. OpenACC takes a different philosophy and says, you tell me where your loops could be parallelized, and I'll choose how I'm going to parallelize them. And the Fortran standard parallelism in our compiler is implemented with the same OpenACC backend on the GPU. And so what that means is I just say every single one of these loops can be parallelized, and the compiler decides how to map that parallelism onto the GPU. It also figures out how to map this parallelism onto the CPU. So this is an example of absolutely no CUDA, absolutely no directives. The only thing I'm changing here is I'm adding the directive to say generate standard parallel code running on the GPU. I also have an attribute for unified memory. It doesn't have to be there, but for me, bookkeeping wise, it makes it easy for me to specify that up front. There's another feature here. There are intrinsics in the Fortran language for doing linear algebra. There's a full list of them on the link at the bottom. This is probably not something most experienced Fortran programmers need because most of you are not writing triple loop matrix multiplication. You're probably using the BLAS already, and we support that, and you can map standard BLAS calls to the GPU. However, if you're going to write Fortran code from scratch today, and you want to really write pure Fortran, then consider using all these intrinsics and know that they will, with our compiler, be mapped onto the CU Tensor backend and run really well on GPU. So this is a case where you can write code that's as pretty as NumPy or MATLAB, and yet is capable of hitting 20 teraflops because it's got a GPU backend glued onto it. And of course, this code is optimized for CPUs as well. If you take that MapMul intrinsic with the right compiler flags, you'll get a BLAS call. So this will be portable performance, assuming all the compilers do the right thing. But obviously, when you're doing dense linear algebra on GPUs, it's almost certainly going to be significantly faster than any CPU. Here's another example. So this obviously Python is not part of the ISO language standard, but standard set. But Python is of course one of the most widely used programming languages in the world, especially for data science. And this is just an example where if you're doing HPC with Python, you're almost certainly using NumPy. And CuPy is a community project to run NumPy on GPUs. I've tried it. It works great. I'm really happy with it. Leagate is something that came out of NVIDIA research and is now transitioned to something we're going to support. And it's not just one GPU parallel NumPy. Leagate is designed to be multi-GPU, multi-node scalable parallelism. And you can see here that there's 1,000 GPUs on this plot in the x-axis, and obviously 1,000 GPUs is many boxes worth of GPUs. And this is obviously, how well you scale is going to depend on your algorithm, your locality, and all sorts of things like that. But what it means is if you're going to weak scale big problems on a GPU supercomputer, you can take advantage of NumPy parallelism and just change your import statement, and that stuff will run. It also may offer more control if you want to do that. But this is something that's really important. You have the data scientists out there running NumPy and buying gigantic workstations with too much DRAM because they can't scale, or because they can't scale effectively because the network doesn't keep up, or their processor's not fast enough, or their memory bandwidth isn't high enough. And this is something where NVLink is a much more capable network than a lot of the commodity networks out there. The GPU memory bandwidth is significantly higher in CPUs. So if you're doing gigantic data sets, use a bunch of GPUs and just continue to use NumPy, and that stuff should work. So just to summarize again, the goal here is we want to make the standards run as possible. If the standards don't give you everything you want, we want you to be able to add directives to that. And if that doesn't get you far enough, we always want you to be able to pull out your CUDA switchblade and do exactly what you want. But within the directives and within the standard parallelism, we want that code to be standard so that it can run on the GPUs effectively, but also it can run on CPUs. This isn't just important because we want people to design applications that are portable. It's also, of course, because now that we're building the Grace CPU, it's really important for us to see that people take advantage of CPU parallelism as well. And so these things will continue to expand in the future. They'll take advantage of our hardware in new and interesting ways, and they'll of course build on the existing unified memory hardware support that makes a lot of this stuff possible. But if you're starting out today, there's no reason why the first book you need to read about GPU programming needs to be by David Kirk and Wenmei Hu on CUDA. That was my first book. But today, your first book on GPU programming can be a book on C++, C++ Parallel STL, or it can be a book on Fortran 2008, or it can be a book on OpenECC or a book on OpenMP. And you can choose the right entry point. into GPU programming, and then you can decide for every piece of code you have, what is the best tool for that purpose, and that'll be supported in your language of choice, assuming it's Fortran, C++, C, or Python. Obviously, there's a lot of other language support out there for GPUs in the world that isn't supported by NVIDIA, but is supported by the community. But we don't want people to be limited to C and C++, and we don't want them to be limited to something like Cuda. We want as many people as possible to be able to take advantage of massive parallelism, including on our GPUs. So that's the end, and I'll take questions now or whenever the organizers want me to.
Yes. Okay. So whoever has questions can please raise their hands, and one by one they can ask the questions. Before that, I have a small question. Hello.
Yeah.
Yeah. So this is something. What I perceive that this is something which is more flexible than Openacc. That you do not need to specify where the code needs parallelization. Compiler will decide that, right?
You need to you need to express parallelism in some form. So, the closest thing to magic in any compiler is Openacc's kernels, which is you just say Openacc kernels and you put it around some code and the compiler does what it can. I will say, as magical as that sounds, it really does work in Fortran nested do loops, because Fortran, Fortran do loops are widely known to be indicative of a code that'll need a lot of parallelism. In the case of the C++ language parallelism, you need to say, transform reduce with parallel execution policy. And the reason you need to say that is because in a C++ application, people use the standard algorithms in many different ways, and they might use transform reduce on 45 elements of a vector, and obviously you don't want to move 45 elements worth of computation to a GPU. You want to move 45 million or 45 billion, and so that's a case where you do need to say, here is an opportunity for parallelism. So there's no compiler recognition here. What there is no specification that this is GPU parallelism or CPU parallelism. It's just this is parallel code, and then you tell the compiler that when it sees parallelism, what the target is.
But see, if you want to sum up the some other features, like if you want to use shared memory.
Yes. So if you want to do GPU shared local memory, right, that is where you obviously, that's a hardware concept, and like all hardware concepts, it isn't well represented in a standard language. So that is a perfect example where if you are using standard parallelism and you discover that you really want to take advantage of those shared local memories, you would either use directives or you would switch all the way to Cuda. But there are, of course, many algorithms where that's not necessary. Right, it really depends.
Right.
And as one example, right, one of the classic algorithms that requires shared local memory is matrix transpose. I happen to really like matrix transpose because of NWChem and stuff. And so I've written it like hundreds of times in different ways. And I've written a CUDA Fortran version of matrix transpose that is incredibly fast. I have also written a one-line version of that using the Fortran intrinsics. Okay. And it runs the same way because the Fortran intrinsic says transpose or reshape this array, and that maps onto the CU tensor library call, which is written by some amazingly smart people that I work with, and they use shared memory. So you're getting shared memory with one line of code. You just don't need to know that that's what you've done.
I see. So that also tempts me to ask another question. Like, is this performance, like comparison of performance between say your Openacc code and the intrinsic Fortran code? is it GPU dependent? In modern GPUs, you are getting it better compared to the older versions.
You mean the standard parallelism stuff?
Standard parallelism stuff.
No.
Is it somewhere dependent on the recent developments in GPU architecture?
Okay, yes. So the unified memory support, in my case, so when you do Fortran allocatable and you tell the compiler that that's unified memory, that will map onto the function call known as Cuda malloc managed, which is taking advantage of the ability to migrate data between the CPU and GPU. So it's true that if you go back to Kepler, I think that doesn't work. I'm not entirely sure. At least it won't work well. Okay. Unified memory support got significantly better with Pascal and Volta and Ampere, with each generation. And so I haven't tried this on Kepler. Obviously, I think people saw on the internet, Kepler was announced as end of life support in a couple months, right? So you may have Keplers. I still have some very old GPUs, but you want to use a GPU that's less than 5 years old to take advantage of the hardware capability that makes all this programming nice. That doesn't mean that it won't work. It just means that it's going to work a heck of a lot better with a GPU that's designed to support unified memory and hardware.
Okay, thanks. And again, my last question, I probably missed it when you were discussing this, that if I have a code which calls a Flux library, now with this ISO Fortran, I do not need to do anything. It will automatically parallelize the Flux library. Is it so?
Well, so what I showed here is actually the mapmo call in the language intrinsics, but I do know because I've been using it. If you use the Cuda Fortran module, that your calls to dgem and the like will be pattern recognized as GPU calls. Okay. So yes, if your code is a whole bunch of BLAS calls top to bottom and no other code, I believe you can just add the use modules, the use kublas statement, and that'll work. Obviously, there aren't many codes that are just BLAS calls, and so for anything that's not in the BLAS, you will obviously need to figure out a solution. Now, that solution can be Fortran standard parallelism. You can take a code with BLAS calls and do loops, and you can take your do loops and turn them into do concurrent, and that code may immediately compile and run well on a GPU. I mean, I have to look at the details to know for sure, but with NWChem, that's basically what I'm doing. In some cases, I'm using the Kublas library calls. In some cases, I'm using OpenACC just because the do concurrent doesn't have every feature I need yet. But in other cases, I'm writing code that has literally no awareness that it will ever run on a GPU. Except when the compiler flags get invoked.
Okay. Thank you, Jeff. And I think if participants have any question, they can raise their hands and we can take the questions later. And you guys can move ahead with your with the later part of the presentations. Is your part over, Jeff? Or
yeah, it's Filippo's turn.
Oh, okay. Thank you very much. Thank you very much for helping us.
So let me share the screen quickly. Should be able to see it. Okay.
It's coming. Yes, we can see. Yeah, please go ahead.
So my talk will move to a slightly different topic, but linked with what Jeff talked about. So Jeff, so first of all, myself, like Jeff, started with GPU computing a long time ago. Both myself and him started with quantum chemistry as a background. I remember probably the first GPU I touched was the one previous Fermi, so around 2009, 8, 9, something like that probably. So definitely long ago. And obviously, Jeff talked about programming model and how to form a GPU resonate very well with me because I've been through all of these phases in a way or another. But my talk is about, my talk was to focus a little bit about what are libraries and some use cases around application, because ultimately, very often, and this is kind of a obvious thing, people don't need to reinvent the wheel. And there will be a library already built that does something that you need, and you just need to find a way to plug this library into your program, your code, just to make it done fast. And NVIDIA invests a lot of time and effort in developing some basic and basic building block and basic libraries, and the community has developed over time a huge amount of third-party libraries and solver on top of these libraries that are used by the end application. So my talk is really about give a slightly overview about what these libraries are, and because of time constraint today, I can't touch all of them in detail, but then I want to move immediately to a couple of use cases and close with something that I will mention briefly. Obviously, the talk is all about software, but I need to at least point out to a couple of things that are key. So the GPU architecture evolved immensely in the past, let's say, 5-6 years. We release a new architecture I believe every 1 year and a half, 2 years. Every time we release an architecture, so for example, the A100 is an Ampere architecture. We bring both hardware innovation and we bring both software innovation as well. So both of them come together. So obviously we try to make use of the best and the latest hardware innovation in our libraries and compiler and software stack.
Filippo, you are not audible.
Can you hear me? Hello, can you hear me well?
Yes, now we can hear you.
Apologies, I don't know what happened. But ultimately, over time, we continue to refine our software libraries, our compiler stack, in order to be the best performance ever. So while hardware evolve, also, even if you don't have the latest hardware, by keeping up with the latest version of our compiler, the latest version of our software, the latest version of our library, you get better performance over time. With Ampere, we added few new things. We added new HBM, we added an advanced NVLink, we added third generation tensor core, we added MIG. Some of these features are wrapped up into a library and are used behind the scene in order to deliver new capabilities. And this is good because, again, that means that the library does a lot of the work for you. So I will touch 4 main topics today. And again, I will try to link all of them in a single story. And then, because the slide will be made available, use some of the keywords that are present in this slide to deep dive into this topic a little bit more further. I will mention about our portfolio of accelerated library, what is and what we've been doing with those. And then I jump straight away to a couple of use cases from CFD, the targeting CFD solver and CFD application. I will talk about an application called PyFR that use cuBLAS. I will talk about an application called OpenFOAM that use both PETSC and MG, that is an additional library that we developed but open source to do adaptive mesh refinement. And then I added last minute this small set of slides, so hopefully I will stay in my slot of time. And these are about SIMNet, because ultimately in our long-term vision, to solve very challenging computing, engineering, and physical problems, we see AI or AI having a role, or having a role to play, and we build a toolkit to basically allow people to build solvers that are AI enhanced or driven by AI. So we start with the Cuda library. So within the Cuda SDK and within the NVIDIA HPC SDK, we ship out a lot of GPU-enabled libraries. We have basically libraries that cover the basic building block functionalities, BLAS, the so-called cuBLAS. We have libraries that cover sparse computation, cuSparse, libraries that cover tensor computation, so multidimensional type of tensor computation. We have cuSolver, that is the equivalent of LAPACK, so SVD, resolution linear system, eigen problem solvers, things like that. We have cuTLAS, that is a new way to combine operator in a way to leverage more low-level the tensor core. QFFT, equivalent of the fast Fourier transform. We have a fast Fourier FFTW compliant type of interface, but also our custom interface that allow to combine real to real, real to complex, complex to real, and all sorts of transformation in 1D, 2D, and 3D. We have obviously more low-level math library, and also because we are a graphical company as well, we have a bunch of primitives that use for graphics, so hardware encoder and decoder and graphic transformation. Obviously, I put here a couple of things. Every one of these libraries behind the hood can leverage the very latest innovation that we put in hardware. For example, Kublas, it can use all the data types that now we support in our architecture. So 14.16, 14.32, 14.16, in various type of integer, mixed precision, B-float, TensorFloat, you name it, there's plenty of them. They obviously they are designed to use shared memory, for example, in a very efficient way, to use the tensor core where appropriate, and also to use a lot of features that are in the hardware. We don't have time to cover all of them. I will focus only on Kublas and QSPAS briefly, and then you catch up with the documentation and all our resources more detailed. So first of all, foremost, just to be, let's say, clear, I mentioned at the beginning, tensor core is one of the key architectural features that we add in our Ampere architecture. This is the third generation. The third generation added more data type, ability to pass more, let's say, matrix size with more relaxed alignment to it. And we enable the majority of our library to use them based on the type of where it makes sense in terms of precision. And here you can see basically a summary. So if you have, if you are concerned about am I using the hardware efficiently, well, are you using the library? Yes. Okay, this is really definitely a great start. Is this library enabled to use tensor core, so to use the majority of the best of the performance the hardware can deliver? This table gives you a brief summary of where is enabled and how. Obviously, for Kublas, this is dense computation, non sparse. For QSPAS, it's enabled the sparse computation as well, which means that I need to fix a few things here. But that's essentially where everything is enabled. Kublas, just to give a little bit overview about the Kublas itself. So Kublas is BLAS 1, 2, 3. So vector, vector matrix, vector, matrix, matrix computation for dense data structure. We add over time more and more functionality, including mixed precision support and including multiple GPU support and batched API. When I mentioned about multiple GPU support in the context of libraries, we have to differentiate two cases. The case where one process can drive computation across multiple GPU. This is what I will call it a multi-GPU computation, so single process, but I can use 1, 2, 3, 4 GPU that I present in a single node, in a single box, that I can access through PCIe, for example. But then we also started to add, which I will not touch today, again, for time constraint, we are starting to add distributed multi-GPU libraries, which means that you're using multi-GPU that are across multiple nodes. So there's somehow magic behind the scene that enable the communication across multiple nodes over the network to do, BLAS or solver, console, LAPAC kind of thing. So often when I mention about multiple GPU, I mean single process, multiple GPU. But we are working on the distributed multiple GPU solver because this is what the developer and the ecosystem is asking us to do. And Kublas is being used for obviously HPC workload, but is also used for deep learning type of stuff. So a lot of deep learning basic computational building block when you do training neural network, but also when you do inference, map very well on matrix multiplication type of thing. So we enhance our library to support those data types as B-float, as TensorFloat, as reduced precision, but also do all sorts of tricks to address, sparsity and things like that. Recently, obviously, we continue to work on features, but recently we started to introduce, for example, better support and optimized libraries for something that is not a power of two and very very particular matrix sizes, very rectangular and not very well, not power of 2, not multiple of 2 type of size. As I mentioned, cuBLAS, you have a Ampere tensor core count for free. The use of tensor core. This is a couple of graphs showing some of the performance where when you enable, when essentially there are tensor core and the right generation tensor core, the performance jump considerably. Take the one in the middle just for reference. In the Ampere architecture, we had the tensor core support for double precision as well for FP64. So compared to Volta, you essentially move from 8, 9 teraflop, the exact number I don't really remember, to almost 16 ones, so a double of X. This is come essentially out of the box for free with no code change whatsoever. You just link the library and everything is done. Also, because of this is happening in computational science a lot, people recognize that they can map their algorithm and map their problem, not always to double precision, but they can start to use very clever mixing precision to get faster results, to leverage hardware capabilities that are present in modern GPUs and things like that. So we also relaxed a little bit what is the standard and the one that's been used for so long time, netlib-driven BLAS type of routines, and we started to add a way to have a more mix and match based on what you need to do. So we created this additional library. It's like an extension of the cuBLAS that allowed to target the right precision at the right operand based on what you want to do essentially, and everything will be mapped on the GPU and done as fast as possible. This mostly has been driven because of again deep learning and the need of use very efficient matrix multiplication around deep learning. But I see the application of this type of uncommon BLAS in a lot of computational science, which might require change algorithm and change a little bit the code. But there's definitely a lot of performance that can be gained by doing so. Another library that I will touch because it will come into play later when I talk about some of the application is cuSparse. So cuSparse is something that we had a while ago, and we've been inspired to buy one of the Sparse BLAS toolkit that was out there, and essentially target BLAS type of operation and LAPACK type of operation, but with sparse data structure, which are very important for a whole series of the computational domain. And people have been looking at use sparse representation of data to save memory and to be more efficient. So we've been working on those for quite some time. We started with the basic type of thing, vector, vector, matrix, matrix, basic stuff. So very much like the sparse BLAS. But obviously over time, we add way more capabilities on that. And now cuSparse is a big library that does mixed precision computation, can handle different type of indexes, can handle different type of algorithm to understand how to optimize the computation internally. It can do batches as well, and it can support a lot of matrix formats and layout. Some of them which I'm not familiar with, to be honest. I know CSR and CSC, but not much familiar with the other. Of course, because it gets complex, the API got complex a little bit as well. So there's a lot of API to ensure correctness and composability. There's a lot of API that a lot of the memory management is handled internally, but there's a lot of API that allow you to reshape and to transform from one format to the other, and then the usual error extension. But one good thing about the cuSparse is that we bake again inside the library the ability to use another piece of new hardware that comes with the Ampere architecture, that is our sparse engine, designed again for deep learning type of thing, but we realize that they can be used for other purposes. Often in NVIDIA, we build a piece of hardware, we build a piece of capability in our architecture for a specific use case in mind, knowing that can be expanded somewhere else, and then we are driven by the need of the communities to essentially build more software on top of it to leverage it in a broader sense. And this is the typical scenario. The sparse density engine inside A100 can be leveraged by the cuSparse in two ways. Can be used to do this simple dense matrix multiplication, so where you start dense, but at the end the output is sparse, or really to leverage in the hardware, where you have a block sparse matrix representation, and because it's block sparse, and there are some constraints there, but hardware dependent, but because of that, through this sparse engine, the internal representation is more compressed, so they can be compressed automatically and then pass through the hardware almost in a dense way. And so as a result, you save both space, but also time in the compute, resulting in essentially faster computation. And this is essentially, it's a tensor core accelerated library. In terms of performance, this is probably one of the few slides that I compare performance against CPU only. Notoriously, people say, okay, doing dense computation is easy, doing sparse computation is much harder. So showing, the cuBLAS is getting tens of teraflop, fine, it's great. But also people are more interested in, memory-bound, sparse type like of computation. This slide is just to prove that with the right effort put in, that we did to our engineering teams, and with the right level of optimization, because we build the hardware, we know very deep how to optimize the hardware, we can get sparse library to really outperform a CPU only type of implementation. And this is a different type of matrices, different scenarios. These are focused on CSR and sparse matrix vector type of computation, obviously. And this is, as you say, there is a gain between V100 and A100, which is good. Usually there is a big factor compared to CPU in terms of time and performance. So this was the library. Again, there probably were many more questions, many more that can be talked about. But I want to take this library and describe to you how those are being used to a couple of more high-level CFD software. I use CFD as an example in this case. I could use other domain, and I grab on purpose contribution that come from external people. So I will show presentation or part of presentation that are actually not mine, are done from colleagues or collaborators, just to prove the point that this is not work that NVIDIA has been doing. We're only supporting it and enabling it over time. So one of the first pieces of series of slides that I want to show come from a GTC of this year talk from a colleague of mine, Nikki, but then that has been working with an Imperial College professor, Peter Vincent, on a CFD solver called PyFR, with since many years. These are just an extract of the presentation. If you want to see all the presentation, you can look at the title and you will find the recording and the slide of the full talk online, which goes also into the physics of the method and all that stuff. I will only focus on what the course does and some of the performance. So PyFR, you can do CFD in multiple ways. Well, that's not there. But PyFR uses a particular technique that's called Flux Reconstruction. This technique was proposed in 2007, and it's a high order accuracy technique, which allows to represent the data and the space via polynomial representation. So, based on the schema you adopt, because there are multiple numerical schema, you can have, different solution point, different inference flux, different correction functions. And again, this is, you can adopt several of these schema. The good thing about this type of flux reconstruction schema is that because it's characterized by good spatial and temporal locality, you can take your representation and map into essentially a very dense type of matrix, let's call it in this way. So as a result, you can map these matrices straight into BLAS. And so you have a high flop per byte ratio. So usually CFD are this, you have this stencil operation. They're very memory bound type of computation. This particular method is actually the opposite. It takes the problem, it discretizes in a specific way, you apply this type of polynomial representation, it dump a matrix, and then you can feed the matrix into the library. And then obviously you manage auto exchange if you go, multi-node. And again, because of this representation, it becomes a very good fit for modern hardware. So they built this code called PyFR with all the features, support single, double, and blah, blah, blah. They also made a way that abstract this code in a way that can use multiple architectures. So they have a backend that also use other GPUs and also CPU as well. But all of this has been done with, I would say, 20,000 lines of Python code that link to CUDA underneath through a markup language called Mako, and then links to the libraries, in this case Kublas, to do the heavy bulk matrix computation. So more or less, this is the outlier of the blocking structure of the code. You know, obviously you have to do input output, you have to define your pointwise nonlinear kernel, things like that. So for what is linearly the pointwise evaluation, they design this They adopt this Mako template language that allow to write high-level, hardware agnostic representation of the equation, and then translate into, in this case, CUDA-C code. But for what is the bulk of the computation that can be mapped on matrix multiplication, they essentially use DGEM and also reduced precision SGEM, and so they can use any vendor supplied BLAS, in this case Kublas. And then everything else goes in the loop. This is an example of Mako, just for the sake of to showcase how it looks like. At the time they started, the whole Python ecosystem for GPU was not yet mature, so they couldn't go for PyCUDA. And I'm pretty sure that if they have to restart today, they will try to use a different approach, but this is what they did. Once the CUDA library is linked, it's compiled, they link with the Python with, I think, Cython, and then they just build everything together and run a native Python application. In terms of performance scaling, I want to show you a result that comes a little bit older, because it comes from a 2016 test case. Can you hear me?
Yes, please go ahead. Yes.
Oh, okay. They come from an old test cases from 2016 that use this multi-blade in this turbine scenario. The only reason I use these test cases is because this has been running at full scale on both Giant and Titan at the time they were available. So just to prove that despite it's a Python code, despite very few lines of code, and despite the mainly libraries, he has been able to run a full scale very efficiently, or as efficiently as can be a CFD code, over 1,000 of GPU at the same time. So this is an example of scaling. Obviously, it's not perfectly linear, but what is very interesting to notice is that they've been able to push these test cases to 1,000 of GPUs. Okay, all GPUs, but these 1,000 of GPUs. I think they tried almost the entire Giant, and they push further than 6,000 on Titan, then more than that. I wanted to highlight here the peak double precision flops. Now, the number doesn't seem very high. It's only 38, it's only 42. But remember, this is a CFD code. If you take a normal CFD code with stencil computation, they use a normal Galerkin method, you don't get 10% of the flops. If you get 10, 20% of the flops, you're very lucky. Here, they push almost double of it, and they can even be higher. Obviously, this result can be taken because it's BLAS and replicated to a more modern hardware, and I'm pretty sure they will go much faster and much higher flop ratio because of the tensor core. But I took these numbers because this was what they presented for the Gordon Bell in 2016. Unfortunately, they didn't win it, but that's fine. If you continue with the presentation, and they also describe the incompressible solver and how they enable it to the GPU, and they show some nice graphics and now case studies with them submarines. But it's all available online for the GPU.
If you have something you can show, I'll be very excited to see the incompressible solver.
Yes, absolutely.
Some pointers.
Okay.
We can go for a few more minutes. Not a problem.
Yeah, I go very fast. I might not touch and leave the last part for reference. The second use case is the CSO is called OpenFOAM. So OpenFOAM is a pretty famous CFD code. It's open source. It's written in C++. It's been used both by industry and academia, and it's been extended in multiple ways by multiple people. So it's been around for a long time. So it's very famous. So interesting enough, OpenFOAM until recently has never had a really well-defined GPU implementation. And the reason is the very complex code, and that's a very complex community behind it, touching multiple parts and multiple forks. But there's been many attempts to add the GPU support to OpenFOAM, and I wanted to list here several of them purely for the sake of reference, because many of them touch different strategies, and some of them have been successful, but they never become mainstream. Recently, in collaboration with Chaos, in collaboration with Cineca, in the context of the Exafoam European project, we've been working with this partner to take a slightly different approach, but make it a little bit more general, to a way that GPU support make its full effort become like a prime citizen into the OpenFOAM ecosystem going forward. So this presentation comes from from Stefano Zampini, who is a research scientist at Chaos in Saudi Arabia. He's also one of the core developers of PETC, which is, I will talk about PETC in a second. And this presentation has been presented during the OpenFOAM conference recently. So it's partially late this year, but I've been announcing with some results from 2021. So what they build in order to accelerate OpenFOAM is something called PETC for FOAM. PETC for FOAM is basically an interface library that abstract the core CFD solver, both the pressure solver and density solver in OpenFOAM, and allow to link third-party libraries into OpenFOAM in a more transparent way. OpenFOAM has its own solver, but its own solver brings its own complexity. If you want to have a GPU solver or any other solver come from outside, PETC for FOAM is this innovation they created to link the two. And what it does is essentially take, brutally, the data structure of the OpenFOAM map to the data structure of PETC, and then you use PETC as a main solver. PETC as a code, which is developed between Sandia, Lawrence Livermore National Lab, and another player, has also a GPU accelerated section of it. So PETC, for who doesn't know, is a portable extension toolkit for scientific computing. It's a massive library that does a lot of things, mostly targeting solving PDE, ODE, and nonlinear solver. So this kind of problem. They added support to Cuda, which actually translates behind the scene of cuBLAS and cuSparse library called automatic, and a whole bunch of other things. So what essentially happened from an OpenFOAM perspective, it's actually very simple. It's very transparent. This is more for user than developer. OpenFOAM has its own format to define which solver and which type of solver needs to be used. For example, the pressure solver, P, or you can define your own. You can tell now to OpenFOAM, once you link this library, okay, I want to use PETC, and these are my characteristics. And when you select the mat type, you refer to the mat type that PETC support, and they have their own format, including backend for COCOS and other, and cuSparse. So you have the cuSparse one. This is the type of preconditioner or the various tolerance, and that's pretty much it. If PETC is compiled with GPU support, he will leverage behind the scene the libraries and some CUDA kernel, but mostly the libraries to get the computation done. And here's again, if you look at the talk online, I think it's been made all available on YouTube as well. But if you look at the talk online, they will describe the results more in detail. What I want to point out is that compared to the CPU only, adding 1 GPU per processor gets around 3 times as average. Of course, this test case probably was not big enough to continue to scale beyond 16. Fine, but there is a good scaling. There is a decent speed up by essentially just linking a GPU accelerated solver. The majority goes into the precondition and the solver itself. There is still a big part of the computation that is the matrix composition, which involves also communication across processes. So obviously it decreases, but it has an effect because it has to compose properly from one data format to the other. And that for PETC was not fully accelerated. So PETC was great, but PETC brings also its own complexity. It's a big package to compile. It's also also complex to understand and use properly because there's so many tweaks and parameters and options. So as a future work, they've been considering to go to something a little bit more lightweight, and basically they would be targeting AMGX. So what's AMGX? Probably heard about this. So MGX is an NVIDIA developed library that does adaptive mesh refinement on GPU, natively fully on GPU. It's an open source library, but we essentially the main contributor, and it's highly configurable. It allows to compose various solver and preconditioner and smoother. It supports also structured methods. Yes, all sorts of Kirchhoff methods and all sorts of smoother already implemented. What's key here is that behind the scene, MGX again use QBLAS, QSPAS, and QSolver out of the box, and it provides a high-level API, which is if it maps to your problem, you just need to use it, initialize correctly, and then you leverage GPU out of the box. Adaptive mesh refinement is something that it's the type of technique you use in a lot of engineering scenarios, CFD, plasma physics, weather sometimes. So it's applicable to a very broad range of scenarios. So what we did in order to make it work with OpenFOAM is basically using the philosophy that was designed by our colleague with this European project, where they want to have a layer that is abstracted, PET-C for foam, in this case, PET-C. We want to reuse this API so we don't touch OpenFOAM, just plug AMGX with something called AMGX wrapper that is essentially like a way to map the data structure from the PET-C world to the MGX. We want to link it to PET-C for foam. So once the library is available and also there, just compile both dependency and everything will work out of the box. AMGX wrapper, again, is an open source project. In this case, not maintained by NVIDIA, but it's out there and it's very permissive license. I go a little bit fast here. So we identify what part of the solver in OpenFOAM needed to be, to be ported, and we need to be adapted to MGX. So we map, we did all the due diligence to understand which MGX solver we need to use and how to set up things correctly. But ultimately, what we come out is also with the understanding that one of the main bottlenecks was the conversion between one matrix format to the other. So OpenFOAM has its own LDU matrix format, which is very custom for OpenFOAM. PET-C and the MGX have their own things. So we implemented a way to transform one into the other. So we create this library. This has been using actually Trust, that is another library, that open source library that we develop and to do operation like radic sort, like sorting algorithm. I actually not super familiar with Trust, but it does a lot of things in terms of array manipulation and structure manipulation to move and do sorting and various stuff like that. So we implemented this, and in order to have also the matrix assembly on the GPU, which was key, because the solver is important, but ultimately what we realized that in the real case scenarios, assembling the matrix before calling the solver were becoming a bottleneck. So we did all the changes. We enable things in the correct way. These are some of the detail and some of the solver MGX enable routine that we developed in PET-C for foam to just link the libraries. And I will show you just an example using this very basic lid cavity example. What we observed is that compared to the CPU on Fortran, we can get up to, let's say, realistic. This is only for the pressure solver, realistically around 3 to 4x. If you focus only on the solver, then in this particular case, it is 70% of the entire execution time. Obviously, the performance is much higher, but overall, the overall work time is actually around 4, the realistic one. But what's again good here is that MGX behind the scene use accelerated libraries, QBLAS, QSolver, QSPAS. So moving to Ampere result immediately in 1.x additional performance gain. So you go around 8 point something, around almost 9x performance compared to the standard CPU solver. purely because Ampere again bring the tensor core and all the innovation we did on the libraries out of the box. So this is great. And just to show some of the scaling, this is where the things are a little bit more clear. You can see, for example, in the strong scaling regime, when I look at the full solve that include everything, you know, in this case it's 2x. But if you look at the solver per se, it goes from 23 to 9 seconds, which is the speed up in MuiltiGPU that we were expecting. And in which scaling is great because the library is well designed. It scales very well in which scaling regime. And you can, for as long as you have enough computation per domain portion, per node, it scales pretty much as expected. So it's a flat profile. So I don't know if I have enough time now. Do we have enough time for just quickly?
Yeah, please go ahead.
About SimNet. So I just want to mention this was not part of my initial idea, but I wanted to add because I've been asked to provide a little bit of idea where libraries and solver are positioned in the GPU ecosystem and how they are used for an application. And I hope the slide that I show some of this idea and allow you to deep dive into this topic if you are interested to. But there is another element here that is very important. That is the way computational science is done is changing compared to the past. And we have been riding the wave of the artificial intelligence revolution, and not just by applying to the classic deep learning problem, but to see if AI can make a difference also in the classic simulation space. And we created this framework, this toolkit called SimNet that I will talk into. So the idea is that, as I mentioned, that we are moving to a AI-based technique to do engineering and simulation science. Before you just prototype, build, destroy, then you create simulation, which is great. It allows you to create this virtual prototype. You avoid to build an airplane engine and destroy it over time just to figure out if the design is correct. You just simulate it into the computer and then you just build and destroy once because it costs millions. But again, because of the complexity of the simulation that we want to achieve, more complex physics, more multi-physics, more coupling, and also become a little bit more data-driven. So take sensor, experimental data and plug into your simulation, your simulated world, and figure out if this is a real match and progress forward. We see for the future that AI-based techniques, data-driven neural network, can be a game changer. Now, when we're looking at how to solve partial differential equation with neural network, there are two approaches that we have to look at. There's an approach that is really data-driven. So we simulate a lot of cases. We take this data and we train a neural network to respond to that particular data. Obviously, you can see immediately where is the advantage here. For as long as you have enough data, you can have a very accurate neural network that replace that solver, but it replaces that solver only for that specific simulation data set. It can be very hard to generalize, or a more physics-driven neural network approach can be taken where you code the equation. This is a very simplified way, but you code the equation into your neural network, and you don't rely on training on data that come from a specific subset of the simulation, and you have to have a priori. And obviously, this physical-driven approach and these PDNN, so physical-driven neural network, are more complex to build, but they have an opportunity to be more general and applicable, or at least with the right level of accuracy and with the right level of tuning, can be applicable to a much broader cases. So, as I say, one of the good of the data-driven model that we are trying to actually go beyond those, despite people have been trying to do already this before this whole deep learning explosion. The data-driven model do not depend on physics, so they can be very accurate for the set you expose to them, but they are not good to generalization. So we built this toolkit called SimNet, and the idea is that it's a neural network solver, or a toolkit, better say, to solve differential variational form of the ODE and PDEs. So it's physics, but also data-driven, and it's a toolkit. So it's not just the neural network per se. We provide all sort of building blocks to allow to digest a geometry, map the problem, define the layer, define custom operator, do parameterization studies, go beyond one GPU, so multi-GPU, multi-node. So it's really become a toolkit that can go in the hand of any engineer and scientist and say, okay, this is some of the things that we've done. What else you can build on top of it to create a neural network that can approximate, and maybe in the future even replace a full solver, a full, for example, CFD solver. This is a schema of the toolkit. As I mentioned, the module goes from how to visualize the results to how to manipulate the data to actually map up, your problem into a deep learning framework. SimNet, we recently released 21.06, is using TensorFlow at the moment. Is mainly target Volta and Ampere GPU. Obviously, it can work on Pascal, but doesn't go as fast as it could be because the previous generation they don't have a very efficient tensor core, but Volta and Ampere have the right one. And then we build some sort of visualization using BTK and ParaView on top of it. And the feature, this is again, I don't know all of them, but it's impressive in such short amount of time how many different types of operators will be baked into SimNet to be able to target a broad range of problems. Obviously, the final question is, fine, this is all cool, how actually relate with the proper solver. So you can go to the SimNet website. There's plenty of studies that we've been doing in several domains, comparing, in this case, still CFD, comparing SimNet output to similar other, packages like OpenFOAM, like ANSYS, like Nectar++, that are, again, different type of CFD solver. I pick one that is CFD related, but it's not one. It's called DeVito. It's developed by Imperial College. It's used for oil and gas computation, and it's designed to basically simulate wave propagation on porous media for obviously extract oil. And there's a little bit of the equation, just put a little of the math. Essentially, the idea was, while DeVito, this framework, can code this equation in a very deterministic way, can we map this equation into SimNet and having a neural network going through the process and give me a result that actually matches reality? And we did a lot of verification and validation on this type of problems. The SimNet team is really on top of it. And you can see here there are a couple of examples. It's far from perfect because it's still very much a work in progress, but it's astonishing how close it becomes to what is simulated with the proper CFD code. So on the left there is what is SimNet, let's say output after certain time. This is what DeVito obtains using a very well-defined method. Well-defined and verified method. And, there is good match, maybe not perfect, but if you look this in the context of a more complex workflow, if you want to run, this is very powerful. If you want to run a CFD simulation for a very long time, you might not want to start in an ab initio fashion, where you start from, entirely from scratch and then use the full solver, because you're interested in the long-term solution. If you know that at the very beginning you have a good approximation of the solution, you might want to start with a AI type of approach, and after a while switch and refine your solution with a proper solver, and then get the result that you want. But by doing this mixed approach, because this goes 100 times or 200 times faster than the normal solver, you shorten your final, time to solution, the overall time to solution of a good factor. And this is another example where, obviously, because this is a work in progress, there is some matching, but sometimes neural networks are not yet perfect and capture all the, the various artifacts and all the various, you can still see that here is not perfect. It couldn't capture this feature that the real simulation code does. Again, this is to reiterate that it's a work in progress. It's a mostly research project, but we started to open up the SimNet to people that are interested to try and take with a grain of salt the result you obtain, because they can still be improved, but it's not yet to a point that can fully replace a CFD code. So it's a good thing. It's helping. It's another way to accelerate code and accelerate solution of an engineering and CFD problem. but it's not yet a full replacement. So with this, I think I conclude. I'll run a little bit longer, so hopefully it's not a problem. So I can take some questions, or eventually through the slide make available more resources so you can deep dive in some of these topics more in detail.
Thank you very much, Filippo. So much information in this talk. I'll request the participants, if you have any question, please raise your hands, and then we can have entertain your questions. Yeah, so I think Professor Rajaram has a question. Raja, please.
Yeah. Hello, Filippo. It's very nice and interesting talk. Especially the last part, like AI-based kind of CFD, what you are guys trying to train, is really remarkable thing. I'm just curious, like this physics-based information, what you are trying to talk about, especially for CFD. Are you guys in a position to implement the Navier-Stokes equation and try to really project onto these planes and try to estimate even on long run? For example, like you have showed unsupervised learning approach, right? Basically is from Kaniadakis kind of groups, what they are trying to look at. So are you guys in a position to implement at this NVIDIA level via GPUs, how to train these models?
So the Somnath team is, so as you probably imagine, this type of approach can apply to multiple, I mentioned CFD here, but you can apply to, electromagnetic type of equation, so the Maxwell equation as well. You can apply to everything that can be modeled through a PDE, and Navier-Stokes is one of them. So I'm aware that they have a very aggressive roadmap in terms of what else they want to add and what type of domain they want to target. We started Somnath as a way to design our own heat sink and the DGX. So that was okay. So we design our own heat sink, and so we take that particular flow problem, simplify it a little bit in terms of geometry, in terms of boundary condition, and then they build on top of it, and they add more and more. And we see now Somnath being used for astrophysics, seismic, CFD of various flavor. I don't know the exact roadmap, so I don't know if we have plans specifically to implement what you ask. I need to ask the product manager. But we receive a lot of, requests and a lot of, can you add this, can you add that? Ultimately, remember that we as NVIDIA, we are not interested. Well, we are interested in the physics, but this is not our domain. We build GPU, we open GPU, and so we try to have Somnath both open and structured in a way that if you are interested in that problem, if you have the knowledge about the problem, you can start to compose what is already there or extend what is already there to match it. I see.
Wonderful. Thank you so much.
Obviously, we understand that this is not easy. This is not like a blast. And if you have a specific research project around this, I'm pretty sure the Somnath is very eager to engage and learn more and help. But ultimately, they might enable you to do it more than us doing it. We did with our own excuse, and we try to create more use cases. But ultimately, we want to create a toolkit more than a final solution. That's mostly our philosophy.
I see. Thank you so much. Thank you so much.
Okay.
Sorry, I forgot to say, Somnath is free of charge as well, like many of the NVIDIA libraries. So you can request it and download it from the website now. That is in general availability. So this is all free. I didn't mention that, but it's very important.
I see.
Okay. So if any question from participants, we can entertain one or two questions. But before that, I think I should ask a couple of questions, Filippo, if it's not too late for you to.
No, it's fine.
Yeah. So first is that what you showed in Somnath, I think it's more important. This is a comment. More important to look into the local accuracy than the global accuracy, because at some locations, if some features are coming which the data-driven solutions are matching. But now my main question is that, do you really accelerate the solutions using data-driven models? That means that does it help in getting better, in some sense, in reducing the computational costs?
So, okay. So in terms of speed, if what the neural network you design with Somnath match is within it's use the features that are tested, so the one that we validated, so those operator map this type of equation, so the problem is well understood and we know it's a good match, then we have a very close agreement between real simulation, ab initio, well understood classical method versus the AI approach. When I say very close, means that within a tolerances that are reasonable, within very small, it's not a perfect bite-wise match. That's never happened, but it's very close. What is not perfect, one of the use cases we observe is that often when you do a simulation, you run very long, as I described, okay? So if it takes like a month with a normal CFD code, I can get to the beginning of the simulation and then refine the solution with a normal solver, can cut it dramatically because Somnath is extremely fast. So if you rely only on the AI approach, you can never some agreement. It's never a perfect agreement. And obviously, someone can say, this is actually correct. Well, this has been done by a neural network. It's correct as it can be. But the real scenario, the real game changer scenario is that when you use these approaches to enhance your simulation, to define the initial part of it, or to essentially, or maybe do ensemble type of stuff, like you design an airplane, okay, you design a wing for an airplane, you don't want to simulate perfectly every possible design scenario of your wing. If you can screen a design space with Somnath and come out with few of these designs that you think are reasonable, because the Somnath and the approach give you confidence that those are okay, they don't diverge, they make sense. Then you can take those and then invest your compute time, your exascale like CFD solver to do those. So this is the type of use that we suggest people to do, not just to rely on Somnath straight away. We're not yet there from that point of view, despite we aim to maybe yes.
Yeah. I have one question, and then there is a question from participants. I'll ask that when you showed the scaling of OpenFOAM, it was something like in V100 you got 9 times scaling speed up compared to CPU using GPUs. Is it that? Yeah. But 9 times doesn't seem to be very exciting. For CFD codes, there are reports of 70-80x speed up.
Okay. So can you repeat the question?
No. So PETC, it shows that around, say, using A100, it is 9x, around 9x speed up compared to single shared CPU code, right?
Yes.
In GPUs.
Yes.
But for GPU-enabled CFD codes, there are reports of 78x speed up. So 9x doesn't seem very exciting. Is it true that I'm missing something?
So if I understood correctly, I was not getting through there. So the speed up you see here, so the speed up that I show about, first of all, OpenFOAM is a very complex code. It has a lot of stuff, and you can build a more complex physics on top of the core solver. And in order to enable OpenFOAM to be GPU accelerated for the broad case of use cases, we focus on the solver. And you get a very good speed up with both, let's see, but especially for MGX, for the solver part. So take this number with a grain of salt in the sense that this is the solver. You may have test cases like this one that is 70% is the solver. You can have an unfortunate case where maybe the solver is only 30%. It happens. So everything has to put into the context. But if we focus on the solver, which is something that every OpenFOAM simulation has to do, independently what kind of geometry, independently what kind of equation they implement, independently what type of domain, because can be normal CFD, can be combustion, can be chemistry, there's a lot of things. So the solver can get as high as these measures we observe in terms of speed up. Yeah, I don't know if he answered your question.
No, I think it's okay.
So obviously, if you take
Yes.
a custom CFD code and you customize it extensively, you can get much higher speed up.
Right.
I agree.
Right. So that's no
for
OpenFOAM it is more complex.
Exactly. So what happened is that the CFD scenario, there's a lot of CFD code that are designed by a research group. So if you have people, there's a research group, I do my own CFD code. I see plenty of those, both Galerkin, both semi-spectral, both Lattice Boltzmann as well as still CFD. A lot of people design their own code, for their own because there is their own research, their own niche research. And then you take what Jeff described, you take the right programming model, the right library, and you push it as far as you want. I've been working on a code recently here in with KTH people. It's a semi-spectral code. We use distributed FFTs. I don't remember how fast it goes compared to the CPU, but it's fully on GPU, entirely. So it must be at least 10 or 15x. But OpenFOAM is really a different beast. It's a community code, a lot of non-domain expert, non-computational scientists, so just engineer using it. And so we had to tackle this part. And obviously, because we focus on this part, the speed up doesn't seem exceptional. But the way it's been done, it might open up OpenFOAM to be used by a much broader range of people, which is what we're actually aiming for.
Yes, okay. Understood. There is one more question from another participant who wrote it in the chat box. Can Simdet be used over software packages like Ansys Fluent? You mentioned something. Could you throw some light?
So, commercial software, obviously we can't come. Of course, we have a relationship with commercial software packages like Fluent, Ansys, StarCCM, PowerFlow, all these kind of big ISV. I can't comment detail of each one of them because it's private. It's if you really have a key question, go to the ISV. But I can tell you, because there are public news about that, I can tell you that some of the CFD software that I mentioned, I'm not say which one, they use the MGX behind the scene. So because the MGX is open source, it's a BSD license, some of these ISV decide to use the MGX to enhance their software. But I cannot really comment on performance and capabilities because it's not an NVIDIA software. It's their stuff.
Okay. So we are at the end of this session. I express my sincere gratitude to both Jeff and Filippo for helping us and working late night to present these excellent concepts on and pointers on the developments in GPU technology in scientific computing. Thank you very much, both of you. And I'll also mention that Mr. Rahul Kumar Sharma, who is in NVIDIA part, was instrumental in connecting myself with Filippo so that this talk could be arranged. So thank you, Filippo and Jeff. And for participants, we'll take 10 minutes break, and at 11:45 we'll start the next session. We'll again discuss about some basics of the packages which they have mentioned in their program, PETC and Hyper, and something more on multi-GPU computing. Thank you all. Thank you all. And
enjoy the workshop. Thank you. Bye bye.
Thank you very much. Bye. Bye. Rahul, morning. So we'll start at 11:45. Maybe first 20 minutes I'll discuss, and then from 12, say 12:05, 12:10, you take the stage. Oh, oh. Okay. Okay. Morning we'll move to the next topic of this presentation, and in this session we'll have two different topics. First, I'll discuss about multi-GPU computing. We have been talking about GPU programming, etc. Last presentation was a detailed exhibition of different GPU technologies in scientific computing. So you can see how extremely large computations can be done using multiple GPUs. And after that, there will be one more presentation by Mr. Rahul Kumar Padhy on the different scientific computing tools and libraries. Like over last day and today, we are talking about PETC, Hyper, Blast libraries, etc. So how to what are those libraries? What are their capabilities and how to use them? That we will discuss after this presentation. So in next one hour 15 minutes, we'll have this couple of presentations. Okay, so what I'll discuss here, what is GPU computing, in specific GPGPU computing, general purpose graphics processing unit computing. What is hybrid computing, and using hybrid computing we can do multi-GPU computing. And there have been cases over last 1 year in the community that people have crossed the barrier of exaflop calculations. That means 10 to the power 10 floating point per second calculations in certain distributed computing system. I'll talk you about that. And interestingly, this is very important because this is an example of COVID-19 research also. So we'll discuss on that. First, the idea was that we talked about parallel computing, multi-core computing, distributed memory computing, etc. And then people realized that if you have multiple processors or multiple CPUs together, they generate too much of heat. So you just cannot put many CPUs inside the same room or many CPUs inside the same computer box. So they came out with an idea of co-processor, that some of the processing jobs of the CPU will be given to something which are a little rudimentary than the existing CPUs, but there will be many of them, so they can take up that. And the first idea was co-processor. Intel came up with Intel Xeon Phi, and there have been many co-processors where you give a job to the CPU, some part of the computing job will go from the CPU to the co-processors, and there are multiple nodes of the co-processor. They will work in parallel and accelerate that computing. In the same idea, but then there have been certain issues, especially Intel Xeon Phi, which was a leading co-processor in the last decade. They are not being sold now. But the another idea came as an accelerator, that it is very similar to co-processor, but it's not like something inbuilt with the process CPU. It is an accessory which you connect with the CPU, and these are GPUs are also like this. And some of the job of the CPU will be given to the accessories by certain memory mapping provisions. So it's not part of the main CPU, but it's connected with the CPU through the motherboard. And some of the jobs will come to the accelerators, and they will do that. So these are not exactly CPUs, and it is seen that graphics processing units or graphics cards in our computers, basically, they are very good in doing that. That some part of the job will come to the GPUs, and GPUs will do that. And if you think GPUs or graphics cards are initially designed for that, their initial use was in gaming. So you think of a computer's screen where you are playing some strategic game, say Rise of Nations. At one location, somebody is building a castle. At one location, a farmer is growing crops. At one location, the revenue collector is going and collecting tax from the farmer. Many things is happening across the computer monitor. And in GPU, through graphics card, this was taken place, that at different location of the display screen is assigned to different cores of the graphics card. Graphics cards were accessories to the CPU, which comes with multiple small processing units or cores, and they're taking up different locations. And then it is thought that if we can utilize these graphics cards for matrix computing, because again, different elements of the matrix have to be touched up by different cards. And it was seen that yes, you can get very good speed up if you can use something like that. Say for coprocessor, you can get 10 times speed up. Similar speed up you can get using GPUs. Over different calculations, you can see that you can get much better speed up. You can get almost 100 times speed up compared to a CPU with a modern GPU. So the idea is that in a single CPU, you do the job serially. When you put a GPU, and you have to have the right software for that, you identify the parts of the job which can run in parallel and give it to the GPU. CPU offloads the job to the GPU. GPU have many small processing units. They work together, and different parts of the matrix computing or different parts of that independent computing units or threads are executed by different GPU cores, and you get a very good speed up. Newer versions of GPUs, we discussed about Pascal 100. Every year, newer versions of GPUs are coming out, and they are getting better speed up. And there are mainly two leading manufacturers of GPUs, AMD and NVIDIA. And NVIDIA has the largest share. Our previous talk was from the engineers of NVIDIA on GPU technology, and it shows that how GPU power has increased over time. They initially developed for game development around 2000. So the GPUs are there from 1970s, graphics cards are there. But around 2000, people identified that they can be utilized for matrix calculations, and they renamed the GPUs as general purpose GPUs or GPGPUs. So at that time, there are different versions of GPUs, ordinary GPUs and GPGPUs. And now almost all GPUs are GPGPUs. And you can see that in peak speed over at the early 2000, GPU outperformed the best CPU by a factor of 4 or something. And if we see the later part of the previous decade, we can see that GPU performance. So this is an AMD GPU, the brown one, green one is NVIDIA GPU, and the black one is coprocessor Intel Xeon Phi. We can see that GPU performance up to P100 is much more, around 10 times faster than the fastest multi-core CPU. And that was the idea, that for CPUs these CPUs are much costlier. It's difficult to maintain these CPUs, and with GPUs you can get better performance. And you can see the performance comparison also, that in GPUs give much better performance. Another thing, earlier GPUs, because they came from graphics era, so earlier GPUs used to give better performance in single precision, smaller performance in double precision. But nowadays, double precision is almost half of single precision, which is theoretically very true. You need less half registers in double single precision, so the speed is double. Well, so this is basically the architecture of a GPU. You have a CPU. GPU is an accessory. It cannot work on its own. You need a CPU which will read from which will take the instruction from the user. You need a RAM which will provide memory to the CPU, and GPU will connect it to the motherboard through an host interface. And inside GPU there is a RAM, device RAM. GPU has its own RAM, own cache, though not big, but some own cache. And then there is an interconnect within the GPU to which multiple streaming multiprocessors are connected. And this streaming multiprocessors has multiple streaming processors or cores. So there are many processing units within which multiple cores are there. In total, in a modern GPU, there are around 3,000, 4,000 cores. Large number of computing cores are available, and some of these cores there is a scheduling of the cores. Some of these cores can do the job parallelly. Once you take the job from CPU, host it to GPU, they work on the job parallelly and can give you a very good speed up. Ordinarily, GPUs are designed for graphics rendering. So even today, if we go back to the previous slide, texture processing cluster, right? This texture is an idea of graphics. Pixel work distribution. So even today, many terminologies in GPUs are related with graphics, though these GPUs can do general purpose calculations, and they are, as we are mentioning them as GPGPUs, they can do floating point calculations which CPUs used to do. Essentially, all modern GPUs are GPGPUs. They can be programmed to deploy the processing power towards addressing scientific computing needs. GPUs are connected to a CPU which offloads compute-heavy jobs in terms of concurrent instruction stream to GPUs. So concurrent instruction streams means what we are discussing in OpenMP threads. So it can launch many threads. CPU can offload the compute-heavy part of the job, and many threads can run in the CPUs. And it is around 2000 we have moved from GPU to GPGPU, and matrix multiplication routines are there in GPUs, and we had discussions on that, and which is required in a large group of scientific computing, and therefore we can do our job in GPU. But there is an issue with working on GPUs which is fading away very recently. See, earlier in 1970s, GPUs were only for graphics purpose. It came into the market for doing graphics, but later it is realized that you can do other jobs like crunching numbers with GPUs. You can do your CFD, your FEM, your molecular dynamics simulations with GPU. However, as it came from graphics purpose, its initial design was based more on graphics. So you need to know how you need to be more adept on porting your codes into GPU. There are hardware issues, how to use the graphics computing like environment for doing the number crunching matrix calculations, etc. There are software issues also. The software used to be little different than our ordinary C, Fortran, C++ programs. But with time, as more and more people are working on scientific computing using GPUs, GPU vendors have put more effort, like the work who discussed earlier, Filippo and Jeff, they work on these areas, that how to make GPU codes more accessible to the scientific computing community, to make GPUs more friendly to the scientific computing community. And therefore, with our ordinary C, Fortran or OpenMP type of knowledge, we can now run jobs in GPUs. But again, this is a different architecture. This is not exactly CPU, so you need to know a little more about GPUs. And I'm not going into that detail. I'm just giving you a pointer. What is GPU? How can you use GPUs? What you can achieve by using GPUs? I'm trying to give you that idea. Another very, very important factor is that GPU is more energy-friendly computing. Data centers where we host computers are known as energy sinks. They take away too much energy to run. They require computers. If you are talking about supercomputers, they require very high amount of electricity to run the processors. As the processors run, they heat up, and then they require almost same amount of electricity to cool down it using air conditioning. So overall, computing is a very CPU computing is extremely power hungry computing. However, it is seen that GPUs, due to their technology, they are less floor space, etc. GPUs are like small, something like accessories, GPU cards. You can put it into your computer, into your workstation. So they can do this crunching with less energy requirement, and they are energy efficient, at least around 5 to 6 times more energy efficient than the CPUs, and therefore even in NSM we have a drive that slowly we should move towards GPU computing, which has certain advantages over CPU computing. On top of that, it's more green computing. So what is in GPU and what compared to a CPU? A CPU has, say, a quad-core CPU, 4 processors or cores. Each has their own control. Each processor has a large L1 cache. Then there are different levels of cache, and finally it is connected to the RAM, dynamic RAM. In GPU, there is a RAM, there is a cache, but the lower level caches, L1, etc., is very small. Control is very small. Rather, most of the transistors are dedicated for computing the numbers, for computing. Most of the transistors present in the GPU core cards are computing cores. There are very small number of transistors for control and caches, so memory handling, running if-else loops in GPUs are difficult because they do not have much control and much memory, cache memory. But as they have more number of cores, when a CPU has 4 cores, a GPU have thousands of cores. Therefore, jobs which are broken down into small, simple pieces of threads can run in. Many of them can run in parallel. and therefore you can finally get a very good speed up. So in CPU you can run limited number of complex tasks because there is good amount of memory, good amount of control, complex tasks can run. In GPU the memory and control is less, so you cannot run complex tasks, and then it's very inefficient if you give a very complex task to run in GPU. But if you give simple task like addition of two numbers, finding out greater of two numbers, etc., and put it into the and then a large number of tasks can go to the GPU. However, for CPU, you can directly write a code and run that in CPU. Programmer cannot directly run the job in GPU. He has to write a program to execute on CPU, and the CPU will be launching a large number of threads into different GPUs. GPU jobs require more granularity and less task dependency. Jobs should run more independently. It's like threaded parallelism. GPUs run threads mainly. Memory access in GPUs is different to CPUs due to small cache, small off-chip memory. Programmer needs to give special attention to on-chip memory which is close to GPU is very small. It has to every time read from RAM. There is very small amount of cache, which sometimes makes it smaller. So we're not discussing this, but you need to know that if you are writing something like a CUDA code, you have to be very much concerned about the memory handling there. And differences in memory handling, the smart ways of working with the memory can give you much better speed performance compared to a naive code. GPU threads are scheduled at the streaming multiprocessors where there are a large number of registers available in GPU which does some latency hiding. If one core is reading something from the memory, another core can be active that time using the register. So there is an efficient scheduling in GPU which also helps it to get good performance as the number of I mean we have discussed that as number of processors increase, performance speed up can fall down, but that can be due to latency, due to overhead, etc. That can be some way masked GPUs. That technology is there. So GPUs provide thousands of cores. There has been a tendency to develop. There has been a drive to develop application software that can scale over these thousands of cores. And you can see that if you go to hundreds of cores, your speed up instead of being 100 probably is 50. So it's always falling down. You go to 200s of cores when you're discussing distributed computing or OpenMP shared memory computing. When you increase the number of cores, speed up try to fall more from 45 degrees up. But in GPU, there is a drive to improve that. In 2006, NVIDIA introduced CUDA, General Purpose Parallel Computing Platform, which will help the GPUs to get good scalability. And it was initially named as Compute Unified Device Architecture, but later they dropped the acronym and used only the CUDA term to tell that this is the API. This is the platform as well as API to parallelize your jobs. There is something which I'm not discussing, I'm not going into detail, but when we talk about GPU programming, though now as Jeff has discussed, you can write your C++ or Fortran code and make it aware that it's running in GPU and it can be automatically parallelized by the compiler. But if you want to do it in the classical way and if you want to get best performance, then you have to use something which is specifically developed for GPU computing, and that's what I'm talking about. That is known as CUDA. CUDA helps you to parallelize your job. To identify, you have to identify the locations which will go to GPU. CUDA helps you to copy memory from CPU to GPU and run threads in the GPU while maintaining the efficiency of the execution. Classically, when we started learning GPU programming, maybe 10 years back, it was only CUDA which we are using, and even today, CUDA is the best way to get GPU performance. Now, this has been already discussed that there are a few libraries which are CUDA parallelized, CUDNN, QFFT, QBLAS, etc. There are some of the programming language like C, C++, Fortran, Java, Python, etc., with which you can work with CUDA. And then with this you can write GPU enabled programs, and there are different GPU chips. There are GPU cards for doing high performance computing, data center applications. There are GPU cards for professional workstations. There are even in your own laptop or desktop, you can put GPU cards. They are not as great in performance as the data center GPU cards, but they will give good performance. And also for embedded systems, mechatronic applications, you get some of the GPU cards. So there are widely available GPU cards, and they are CUDA enabled. That means you can write a program using CUDA and port it into those cards, and they can give you performance. So what is the CUDA programming model? It is some way similar to OpenACC, that you identify the serial and parallel parts. In the serial part, it runs in the CPU. When the CUDA kernel is called, then compiler knows that it is a parallel part. The CPU puts the jobs to the GPU, and multiple threads, a large number of thread blocks are created, and the job and multiple threads work in parallel inside the GPU. Once this is done, control again comes back to the CPU. CPU runs it, and again, once required, it goes to the GPUs. So this is, but this is not a synchronization step. CPU can launch the CUDA kernel and can do something else also. CPU can be separately active over this region also if required. And I'll show there is an easy, like OpenMP, there is another version, another API, OpenACC, which helps you to write GPU parallel jobs with less difficulty than writing the CUDA code. So there is an example of OpenACC program, and it is shown that compared to a 64 processor CPU, GPU gives 3 to 4 times speed up for running Gauss-Seidel SOR calculations. And if we can see that how much time is taken for different memory handling and kernel execution in GPUs. And we can see that initially the memory handling time has almost remained constant over different versions of GPU. K80 was an older version, then came P100, then came V100. But the calculation time drastically came down when we moved to the newer versions of the GPU. And you can see that compared to a single processor, so so this is not a CPU, this is a GPU base. Let's not look into that. But yeah, we can see that compared to multiprocessor CPU, GPUs can give better speed up, and we can get 70 to 80 times speed up in in-house codes if we use GPUs efficiently. Now comes the idea of getting much higher speed up, and in case you have a very extremely large job, you are doing billion node calculation, you are looking into some system to its fundamental most physics point of view, that everything you will resolve by computing. And then the idea is that you develop a system which has a distributed computing architecture, different computers within their memory, and within that you again develop another level of parallelization, that you give the jobs to one computer, to either to a CUDA card or to a multi-computer system. So this is called a hybrid parallelization, which is again, GPU is a shared memory system, they use the same memory, but you make a distributed memory, you are using multiple GPUs. You make a distributed memory system with different CPUs and then connect different GPUs on that, and by that you can keep on increasing number of GPUs and can really do very large calculations using this. So the idea is that there will be different CPUs. Each CPU is connected with the GPU, and MPI will be used to distribute the job among the CPUs. CPUs will communicating among them, and in between, within each CPU, the job will be given to a GPU. So this is like that we using MPI, you can copy. First, you can copy the data from GPU to CPU, then use MPI from CPU to another CPU, and then, so this is an MPI calls, then again copy the data from that CPU to that GPU. And you can actually, even with the recent technology, you can actually eliminate that MPI based data transfer by NVIDIA GPU direct technology, which helps to use multi-GPU computers, that from GPU memory to GPU memory, directly data can be communicated. However, it is basically a distributed data among different CPUs, because GPUs cannot work alone. CPUs only can put jobs into GPUs. So data has to be distributed among different CPUs, and each CPU will offload some of the tasks to the GPUs. So this is basically what we talk about hybrid computing. It has both distributed as well as shared memory architecture. And now we can see that using multi-GPU, right, we can get a very good amount of parallelization. So this is single CPU core jobs versus the dotted one was the time required for multi-CPU code. And then we added GPUs with the CPU. So this becomes a multi-GPU code. And the parallelization is almost constant. That as many, it's like a very transparent parallelization. As many GPUs, as many CPUs are there, the way the job scales in the CPUs. If you put GPUs, it will be multiplied by a factor. The factor given by the GPU speed up. And people have done some of the very large calculations, like 8,000 GPU calculation with very high speed throughput. Throughput is almost remaining constant using GPUs. There are multiple examples like unstructured CFD code, DNS conversion using Fun3D. There are many examples where people have used thousands of GPUs to run an extremely large problem in parallel. And now the question was that if we can do exascale computing, it is seen that many problems like turbulence, dark discovery, etc., they require exascale computing, and that requires 10 to the power 18 floating point operation per second. However, there have been certain challenges, and exascale, many countries, including India, US, Japan, many countries, there are consortium that you need to break this exaflops calculation. You need to make a system which has the right parallelization, which is the right memory, which is where you can provide the right amount of energy to run so many computers, and you need to break the barrier of 10 to the power 18 floating point operation per second. Till June 2020, no supercomputer shown exascale performance. However, we got into a folding at home project, which is all of us went to work from home mode, and it was difficult to maintain the lab-based supercomputing systems also. Some of the central systems they are maintained, but as we went to COVID-19 lockdown, it was difficult to maintain everyone's own lab system. So people thought that they will sit down at home and connect their computers. Even if you are going to lab, you connect your computer through internet to another computer. And citizen computational scientists working in different fields can devote some time of his own for computing, connected their computers through internet and made a very large cloud of computation. And then it combines CPUs, GPUs, PlayStation, Sony, and then they simulated what is happening for 0.1 second of the viral proteome of COVID-19, that spike of COVID-19, which finally came into the vaccine development. What is happening to the spike protein of COVID-19 and over the COVID cryptic pockets, etc. And then they broke the exascale computing part. So people from different parts of the world contributed their computing time via internet. Connection is slow, true, but they came up with an algorithm which actually broke the exascale computing part and devoted a very useful information, came up with a very useful information in COVID-19 research. And finally, the output is the knowledge about the COVID-19 spike protein behavior, which is translated into the vaccines, Moderna, AstraZeneca, or other vaccines. This research is extremely benefited by folding at home projects. So there are ways of doing things. If human civilization thinks that they want to progress, there are ways of doing things. Even if you do not have access to a great supercomputer, you can if you are smart enough, you can make the systems, and if you join our hands. So this is a very good example. We should talk about this at least at that situation when you are going through the pandemic. And this is a case study that how supercomputing can really help us to get better things for them. So this is the performance of folding at home compared to all the available supercomputers in June 2020. So this actually broke exascale barrier, where the others are 10-20% of exascale barrier. Well, so I came to the end of my presentation, and now Rahul will demonstrate some of the solver packages which as users or programmers you need to know about. We have discussed about basics of GPU architecture, some small pointers on CUDA I have given you, what is hybrid computing, and then showed an example of exascale computing. Okay, thank you all, and if any question you can raise your hand. Yes, Priyambada, let me unmute you. Yes. Sorry, Priyambada, you can ask question. You can unmute yourself and ask question. You're muted.
Yes, sir. Sir, am I audible?
Yes, yes, you're audible now.
Sir, I tried to parallelize our code using OpenMP, but the time execution is not coming out very proper. So could you suggest some platform or resources for
Where are you doing it in your own computer?
Yeah, I have a 4-core CPU.
How is the performance coming out?
So it is actually not, I mean, it is.
I mean, in 4-core, even in 4-core CPU, you should get some performance if you're written the code correctly.
So maybe sir, that's
good thing, a better thing will be, it's difficult to discuss it here. If you write to me, I can look into it later.
Definitely, sir. Sir, I'll do that.
Okay.
Sir, any good resource for matrix?
Matrix? Sorry?
Any good resources for parallel solving matrix calculation?
Right. Yes. There is Michael J. Quinn's book. So let me share my screen again. Oh. Michael J. Quinn parallel computing book. Yeah, you can note down the name. It is Parallel Programming with C and MPI and C, MPI and Open C. Parallel Programming in C with MPI and OpenMP. Michael J. Quinn. This book is available, freely available online.
Okay, sir.
There are many other books, but this is a very good book. You can look
Thank you so much, sir.
Okay. Then we have Sutitha. Sutitha, you can ask question. You can unmute yourself and ask question.
Hello.
Yes.
Yeah. So I thank you for the very nice talk, and your last slide was very inspiring to see
Right.
The exascale barrier being reached for a good cause. But I was wondering, is there any downside to this transition we are all planning to make towards a greener computing framework using GPU? Is there anything, any quantitative study being done on the?
I'm really not sure, but you can. There are studies. There are studies. There have been.
What is the impact of to the global heat budget of?
Yeah. There have been a number of work. You have to search it a little bit. There have been a number of work on heating by the data centers, power hungry data centers, and especially environmental activists I'm telling about data centers. There have been number of work, but for GPUs, people are showcasing GPUs for green computing. You need to search. Even if you go to Google Scholar, probably you'll find some papers on it.
I know I can do. I just curious that
Yeah, I mean, I collected I showed one slide, one figure here. I collected it from some paper. I forgot. I think I should have mentioned it. Yeah,
Okay.
this is Carl Roop, carlroop.net. So he has given, yeah. I'll upload these presentations. You do look into carlroop.net and he gives a lot of discussion on advancement in computing. You'll get some idea from there.
Okay. Thank you. I had one technical question also.
Yes.
That you showed a slide of comparison between the Intel Xeon Phys and maybe the latest generation of GPUs.
Right,
and
this one.
And the speed ups, relevant speed. Yeah, this one. So, could you comment a bit on like what this was, like the problem size of it, or?
Oh no, they have not given it. I think it's the benchmarking. I don't think it's on a particular problem. It's linked.
Because I have like doing this study at the Lawrence Berkeley National Lab in the US, comparing between Xeon Phys and GPUs using their latest Perlmutter architecture, and I mean, the performance really depends on the size of your problem.
Oh, sure. I think this is benchmarking using LeanPack. I never worked on CNC, so I just got this.
I work on DNS codes only, but I'm not sure about GPU performance. But Xeon Phi.
If you want to know about Xeon Phi, in CDAC, Dr. Vikas Kumar's group have worked extensively using Xeon Phi.
Right.
You can write to Dr. Kumar and
I'm in touch with the CDAC people. Yeah. Okay, thank you so much.
Thank you. Yeah, Archana, let me make you a presenter. Yes, Archana. You have to unmute yourself. Yes.
Yes, sir. Good afternoon, sir. Actually, I'm very beginner in this parallel computing or HPC working. So to learn more, so what should we have to do for this?
To learn more.
Yes.
See, I think good thing will be learning MPI and OpenMP. You can do it yourself if you want to learn it. There is a so I think we had a participant who was earlier in Lawrence Livermore Laboratory. Lawrence Livermore Laboratory has a very nice tutorial page on MPI and OpenMP. So I'll share that with you. And you can go through those tutorials and you can practice yourself, but you need a platform in your computer itself. You can work on it, and at least for the learning purpose you can use your own computer, but then you need a platform.
Okay. Yeah, thank you, sir.
Thank you. So we will move to Mr. Rahul Padhy's presentation. Okay. Let me turn off my screen. Yeah. And Rahul, you can share your slide. Okay, so
yes, sir. Rahul, I hope my presentation is visible.
Yes, it's visible. Rahul is a project. It was visible. You have taken share the presentation, right? Rahul is a project engineer in our Nodal Center. He is working on different scientific computing and AI-based applications over last 1 year or more than that, and he will demonstrate you how some of the scientific computing libraries like BLAST, PETSI, Hyper, etc. can be used for actual coding purpose. Over to Rahul. Please go to presentation mode, Rahul.
Yes, sir. I'm trying to do that. I hope it is visible, sir.
Yes, it is visible. Please go ahead. It is visible.
Good afternoon. In this session, in this presentation, I am going to talk about scientific libraries for matrix computation. Presentation, we are going to discuss about numerical algebra. What are the techniques and why do we need to use libraries instead of writing our own code? Advantages of using the libraries. Some commonly used linear algebra libraries like BLAST, LePack, Hyper. and for which specific cases we can use them. Then we'll discuss these libraries mentioned, and these are the foundation to build other libraries and are widely used for linear and non-linear equation solutions. So in particular, we're going to discuss packages libraries which do linear and non-linear algebra. To solve linear or non-linear system of equations, computing eigenvalues, there are different techniques present. These techniques are present for a long time, and we can write our own code based on these techniques. So why do we need to use libraries? These numerical computations are done on computers, and libraries which are developed based on these techniques are optimized till the last line of code. The library codes have been optimized for efficient storage and fast processing for several years by the experts. So if there is a library present which can do the desired calculations, then it is recommended to use them. We just need to familiarize ourselves with the nomenclature and the terminologies. By using the libraries, the amount of code we need to write reduces significantly. We just need to call the routines and provide our input. As amount of code reduces, the amount of time we invest in debugging reduces significantly. If we want to change our method, then we can easily change it. Suppose we want to change our solver or preconditioners, etc. We don't need to write the whole code again. So as these are tuned and optimized implementation, and some are tuned specifically for a particular hardware, that's why they are a lot of times faster than our naive implementation. The implementation we basically write without optimizing. So best performance is observed when the code is system and processor specific. We have here is a naive implementation of matrix multiplication, which is written in Fortran. We have three loops. Size of the matrix A and B are n cross n, and we have computations of the order of n cube. Here in this graph plotlet, as you can see, it's flops versus n, the size of the matrix. Flops is floating point operations per second. Flops is an important parameter for measuring computer performance. In black color, the naive implementation is shown, which is written in Fortran. In red, the Fortran matmult function, which is inbuilt function of in Fortran. In green color, the reference BLAS library implementation, which can be found from the Netlib website. Netlib is a repository maintained by University of Tennessee and Oak Ridge National Lab, and this implementation is freely licensed. The reference BLAS is not optimized for a specific hardware, whereas the BLAS from Cray Lipsy, Cray vendor, plotted in blue, is optimized for Cray XE series computers. There are several other optimized versions of BLAS also developed by different computer vendors. In this graph, as we can see, the BLAS from Cray Lipsy vendor is 5 times the floating point operations is 5 times the BLAS reference, and for the same BLAS from Cray Lipsy, it's 10 times the floating point operations is 10 times from our naive implementation. So we can see how the codes are faster for these libraries. There are many ways to optimize our code. Here are a few. First is we have to prevent cache miss issues. We need to prevent cache miss issues. Let's say, for example, we are performing a matrix vector multiplication in Fortran. For row major axis of the matrix, when we multiply rows of the matrix with a column vector, there will be cache miss, especially for large matrices, because Fortran stores a matrix in column major order. So we can multiply columns of the matrix instead of multiplying these rows. So cache miss slows down the computation, as cache memory is faster to access. So then coming on to loop unrolling, for a matrix multiplication, for example, we fetch entire row and column of multiplier matrix to obtain one element of a product matrix. To use a combination of multiplier matrix for calculating many elements of product matrix, we can get a faster speed. Then coming on to cache blocking. Instead of loading individual rows and columns, we can load blocks. This helps to reuse the same cache data for several computations. And as parallelization was discussed by Somnath sir before, we can decompose the kernels, which are compute heavy parts on a distributed architecture like GPU, where several threads compute simultaneously. We can develop code for parallel computation, hence we can optimize it. Along with this, there are several other ways to optimize our code, and to do this all by ourselves is a very difficult task. Hence, use of library is recommended, which already include these optimized techniques. So these are the most commonly used linear algebra libraries. There is BLAS for solving dense linear systems. There is BLAS, LinPack, ISPack, and LabPack, and its variants. BLAS, as we are going to discuss it next, is the foundation of other libraries. LinPack was developed for numerical linear algebra in 1970s and early 1980s for vector and matrix operations. Its parallel version, known as high performance LinPack, was used to rank supercomputers in top 500. ISPack was developed to calculate eigenvalues and eigenvectors for specific types of matrices. LinPack, which is originally written in Fortran but has extensions to be called in C, C++, etc. There are variants of LinPack, Atlas, MLIB, etc. Coming on to solution of sparse linear systems, PETSI can be used to solve in single core, multi-core, and distributed systems. If the problem is too large, which contains large number of elements or nodes, where we get from the discretization from FEM or FDM and finite volume discretization problems, then using a distributed memory system can be a practical way. Coming on to BLAS, it stands for Basic Linear Algebra Subprogram. This is the foundation to develop highly optimized libraries. One really good implementation, as it was discussed in the morning, is Cuda BLAS, developed by NVIDIA for GPUs. The BLAS has a de facto standard, a general interface for nomenclature and implementation. Higher order operations like Gaussian elimination, etc., which can be done by LabPack, is built on BLAS levels. So BLAS has some categorization of levels. There are levels of BLAS routines. As we go to higher levels, the routines gain in complexity of structures and operations. The level 1 contains operations of the form y is equal to alpha x plus phi, where x and y are vectors and alpha is a scalar. L1 includes, the level 1 includes scalar vector operations, dot products, vector norms, etc. These operations, they have low computational intensity and low data reuse, and the speed is limited by memory bandwidth. So to summarize, the flops, the floating point operations per memory reference is quite low for BLAS level 1. Coming to the level 2, this contains matrix vector operations faster than level 1, more flops per memory reference, is of the form y is equal to alpha x plus y, where A is matrix and x and y are vectors. The level 3 contains matrix operations, solving system of linear system of equations, and the complexity is of the order of n cube, and a lot more flops are there per reference memory. So BLAS level 3 is recommended. Nomenclature of BLAS routines. Here, as you can see, the prefix stands for the data type. Like S stands for, can be single precision, double precision, complex, and double complex matrix. Here S dot means single precision dot product, and ZAXPY means double complex AX plus Y operation. For level 2, we have the prefix here DGEMV. D stands for double precision, and G stands for the type of matrix, and MV stands for the operation that we need to carry. Like here, it's MV stands for matrix vector multiplication. And similarly for level 3, we have the similar nomenclature. MM stands for here in SGMM, the S stands for single precision, G stands for general matrix, and MM stands for matrix multiplication. Here is an example. Let me take an example of implementation of DGMM code written. This is written in C++. Here M, K, and N given to determine the size of matrices A, B, C. Dynamic allocation there. Here we are using CBLAS DGMM, which is the implementation of BLAS in DGMM BLAS in C++. Allows this gives us preference to store our matrix in row major or column major or order. It depends on the user if you want to do transpose of matrix or not. Then M and K are the sizes. Alpha is the coefficient of where alpha AB plus beta C is equal to C. Here alpha is the coefficient of AB, and now here we in A, if you want to give the whole matrix, then we can for computation of matrix multiplication, we can pass on A, or else we can give subblocks of A. I'm going to demonstrate in the next slide. Here logically we provide a 2D matrix, but physically it will be stored in consecutive spaces in row major or column major. Let's say instead of giving the whole matrix A, we want to give it subblock for multiplication. Then we'll provide the address of this subblock represented by 3, 2, 4, 2, and 4, 4 for multiplication. Then address of the element 3, 2 where this subblock starts, and 3, 2 and 4, 2 will be in 2 consecutive storage. Then we'll give M is equal to 2, and here after a gap of the leading dimension will be there for the next element, as we are giving this subblock for multiplication. So by providing these the routine, we can multiply the subblock. Coming on to LAPACK, it stands for Linear Algebra Package and has subroutines for solving linear systems, matrix decomposition, and factorization. Nomenclature almost same as BLAS. It has 3 categories of routines: driver routines, computational routines, and auxiliary routines. Driver routine stands for the operations we need to perform, and these auxiliary routines, it has auxiliary tuning parameters to fine tune it for optimal performance on target hardware. It also has a C interface called LAPACK E, and the naming scheme of LAPACK is similar to BLAS, where the here P mentioned stands for the type of numerical constants used, and MM stands for the kind of matrix to be operated, and A stands for the actual algorithm. For example, if we have DGSV, D stands for double precision, G is the general matrix, and SV stands for solution of linear system of equations. So DGSV computes solution to a real system of linear equations. Now solving AX is equal to B using LAPACK, it does decomposition of A by partial pivoting and row interchange. Here A can be decomposed into a pivoting matrix, lower triangular matrix, and upper triangular matrix. This can work the same way for I have demonstrated for BLAS DGMM. It can work also same way for multiplication of the subblocks if we don't want to give the whole matrix for the multiplication. So one good thing about this is once A is decomposed, we can calculate for any number of B. Like if A is decomposed for any B, no further decomposition is required. Moving on to Hyper, it stands for High Performance Preconditioners and can solve for large and sparse linear system of equations on massively parallel computers. It uses parallel multi-grid solvers for structured and unstructured grid. Compared to traditional methods, multi-grid methods take less amount of time to converge. There are some linear interfaces in Hyper. I'm going to describe that. Before writing the code, we have to choose the linear interface solver, matrix storage, etc. There are 4 interfaces in Hyper. So these are structure grid, it's called struct. It contains rectangular grid, and we have semi-structured called struct has, for example, block structured grid, and finite element interface has unstructured grid, and we have linear algebra interface. If our problem doesn't fit into the above three, we can the last resort is linear algebra interface. It has general solvers and preconditioners. It's not specialized for a particular problem, so the user needs to do a lot of work in this linear algebra interface. So let me give a structured grid example problem in Hyper. If we have a Laplacian of u is equal to f in the domain, and we have the u is equal to 0 on boundary. So as described, there are 4 basic steps. First, we have to set up the grid and set up the stencil. This will constitute the basic structure. Then we'll set up the matrix and set up the right hand side vector, that is b, x is equal to b. In the grid setting, in Hyper, suppose we have a large grid and we have a large number of processors. Then what we will do is we will partition the grid and divide it into the number of processors. So I am taking one grid and I will discuss the code for that grid, and it will be same for the other processors also. So for, let's say, for processor 1, I have taken a grid, and this grid has a finite volume discretization. So computing unknown at a point, let's say point P, where we have to calculate the unknown. The discretization in left we have west for 2D discretization. In right we have east, and in up we have north, and down we have south. So with this is 5-point volume discretization, finite volume discretization. So with this grid, it is the union of the LHS, the left hand side grid is the union of these two right hand side grids. So if we want to build this grid, so for building this smaller grid, that is 2 cross 3 elements, we have to give the coordinates of the corners, which is -3, 1 and -1, 2. And for this, the larger grid, we have to give the coordinates of the corners 0, 1 and 2, 4, and then we'll assemble. So here, as I have said, we'll call the hyperstruct grid object. Then after that, we'll provide the dimension, as we have the 2-dimensional problem. So these are the 4 corners, as I've discussed in ILO 2 cross 2 and IF 2 cross 2. These are the 4 corners we need to give for grid extents in the grid extents function. Then after that, we'll assemble the grid, which is the union of these 2 small grids. So coming on to setting up the stencil, at a particular point, if you want to write the discretized equation, we need the 4 other neighboring points. So for stencil, we need to provide those coordinates with reference to the point with respect to which we are considering the equation. Then after that, we have to, which is given in, after that we have to give the abstract offset, which is the actually specifying the distance from the origin. Then we'll create the stencil for S0, S1, S2, S3 and S4. Then setting up the matrix, we'll assign the non-zero values and initialize the matrix as we provide the coefficients for X is equal to B calculation. Then we set up the matrix in 2 calls for these 2 partition grids for the 2 boxes. The coefficients here we have, the user has the choice if he wants to give constant coefficients or the coefficients can be variable. And we'll assemble the grid. For fixing the boundary condition, we have taken a Dirichlet boundary condition case. So we are assigning values for coefficients of S3. We have assigned S3 0. So after that, we'll similarly set up the right hand side vector. Right hand side vector is the B vector, which is AX is equal to B in AX is equal to B for various grid points, and we'll set up the matrix. So next step is to solve the system of equations. We can use solvers like Jacobi, SMG, DF, MG, and all those have almost similar steps to solve. First, we have to create the solver object, then set the parameters like tolerance between the iterations, then set up and solve the system. After that, we need to extract the solution for different grid points and then destroy the solver. So moving on to the solution of nonlinear system, here are some libraries we can use. The most commonly used library is PETC. I'm going to talk about PETC now. So how do we arrive to this system of linear equations? Suppose we have a PDE, then the PDE can be discretized using FDM, FEM, many discretization methods are there. And after discretization, the system of linear or nonlinear equations arise. Here is an example. We have the PDE with space and time, it varies. And we have discretized the space using backward difference and time using forward difference. And then after this discretization, this PDE becomes an algebraic equation. So this algebraic equation can be linear or nonlinear. So depending on that, we need to choose our solvers. So PETC stands for Portable Extendable Toolkit for Scientific Computation. It is a parallel toolkit to solve PDEs. It has Krylov subspace solvers for linear system of equations, and also it has SNES, which stands for Scalable Nonlinear Equation Solver for solution of nonlinear equation. It offers interface for profiling, debugging our code, etc., and for post-processing also. So why do we need to use PETC? If suppose we have large matrices and vectors, after discretization, we have billions and millions of nodes. So one node cannot do all computations in a faster speed. One node definitely can do, and it cannot store all the elements. So the domain gets decomposed into multiple processors in a distributed system, and this is a practical way to do it. So here is an example of solving nonlinear equation using PETC. Consider this nonlinear equation fx is equal to 0. We have the approximation at a particular iteration xi, and delta x is the correction. So we have f of xi plus delta x is equal to 0 as we have added the correction term. So the solution for the next iteration should satisfy f of x. So by Taylor expansion and truncation, we have this Newton approximation mentioned in 1 and 2 equation. We need to solve these two equations. Suppose we end up with a nonlinear system of equation, we can use SNES available in PETC, or if we have a linear system of equation, we can use Krylov subspace method. So the function, we need to calculate also evaluate the storage of the solution vector, the residual vector, and the Jacobian required in this problem. So moving on to the code, here is the code. I will give you a brief description, won't go into the details. So in the initial few lines, we are doing the declaration and initialization of the variables from 34 to around 47. Then after that, we are initializing the PETC environment followed by MPI calls. We can use it for a single processor also, but we need to configure it to set the MPI is equal to 0 for that. Then after that, create the nonlinear solution objects here. SNES, and create the vector objects. Then from 84 we are setting the Jacobian matrix. Then from line number 106 to I think 118, we are declaring the KSP object, either Krylov subspace object or the SNES object. Parameters are given like tolerance, etc. So after initializing the parameters, we can solve by one function call from SNES, and here is the post processing and destroy code. So to summarize the functionalities of PETC, it has Krylov subspace solvers for linear equation and scalable nonlinear solvers for nonlinear equation. It also has preconditioning objects, has callback functions for evaluating Jacobian, and solvers using SNES solve. It is built with parallel processing and is also MPI enabled. Are the references. We can use the netlib repository and MSc repository for Petsy and Hyper. Yeah, thank you. Yeah, is there any question? Then let me know.
Rahul, I think there are two persons who raised their hands. Let me make them presenter. Sarif and Sarifuddin and Adarsh. Please unmute yourself and ask questions. Adarsh?
Yes, sir. Sir, my question is, can you discuss a little bit about Fortran and what is subroutine? Where we use this Fortran? What is the main purpose?
Fortran is a programming language.
Yes, sir.
Rahul, go ahead. Rahul, go ahead.
Yes, sir. Fortran is a programming language. We can write like we have equations and PDEs, but to make it in a way that machine can understand, we discretize the equations and write it in Fortran for computation.
And so what is the difference between 77, 80 and 90?
No, similar to C, Fortran is a programming language and it has different versions. Its capabilities in 77 was an older version. It's kind of the year in which it was released. And even now we talk about Fortran 2015. Fortran 2000 was there. It is based. It had the different versions of the programming language. Initially in 77 there were no dynamic memory. You could not allocate the memory. You have to work with a fixed array size. But in 90 you can use allocation. So similar capabilities came later. It is similar to C. It is a programming language. It's called for formula translating language. So it is basically for scientific computing. For this language, you can write your programs using.
And subroutine is same as code.
Subroutine is something like a function. Inside your main program, you call different subroutines. Subroutines are subcode, parts of the code.
Okay, sir. Okay, sir. Thanks.
Sarifuddin, do you have any question? Raised hand. No, maybe. If anybody else has any question on this. Okay. Saudish Behera. Okay, let me make him a presenter. Yes. Saudish, please unmute yourself and ask the question.
Good afternoon, sir.
Good.
Am I audible?
Yes. Go ahead.
Sir, just a small question. In your presentation, there was a slide on CPU versus GPU, comparison. So there was why we are not using the L1 cache in GPU?
What why you are not using?
L1 cache.
No, L1 cache we use in GPU. See, when the GPUs came there, L1 cache, there was no L1 cache. Okay, GPU has a different structure compared to CPU. GPU, let me show my slide once more. Wait a minute. Sorry. Rahul,
Yes,
can you stop presenting?
Yes, sir.
Yeah, so if you see the structure of a GPU, you will see there are many computing cores. There is the RAM, there is L2 cache, and there is very small amount of transistor or storage space available for L1 cache. So initially when GPUs came there was no cache. You have to, L2 cache was there, there is no L1 cache. You have to directly read from memory and then you have to take care of the memory management. But now there is L1 cache. However, this is smaller than the L1 cache available in CPUs. So memory access is difficult here because the idea in GPUs to put more computing cores, they have provided less cache. That is that. And from the cache area also you can make something called shared memory. You can identify some location where you can populate some memory and keep it always for the calculation. It is not like cache that it will be erased, it will stay there. So in combining this, cache is usually small in GPUs. It is by the structure itself, hardware.
Okay, sir. Thank you, sir.
Thank you. Okay, so if no other question, then we'll close this session. And so the matrix computing, CFD or computational mechanics type of computing, those discussions are over yet. But if you have questions, we can discuss it later. Next session will be on probabilistic calculation, that is Monte Carlo method by Professor Pralay Mitro, and we'll start from 3 p.m. Okay, thank you all.